Hi, this is Saurabh, and I am going to introduce our ICCV paper. DiffTAD, Temporal Action Detection via Proposal Denoising Diffusion. This is a joint work with University of Surrey and Imperial College London. In this work, we showcase how generative models like diffusion can be integrated with discriminative tasks like temporal action detection. Let us revisit the task of temporal action detection. Given a video, we are entitled to ask two simple questions: what is the activity? And when is the activity occurring? This leads us to solve two subtasks, which is action classification and boundary regression. This can be considered as a one-dimension variant of object detection. Existing TAD approaches are all based on discriminative modeling paradigm, where they either deal with anchor-based models, proposal-based and proposal-free-based models. Such models have a fixed inference output for the same video each time it is run. However, these models fail to model stochasticity or dataset bias present within the dataset due to faulty annotations. As a result, the performance of TAD approaches are still low as compared to object detection. This brings us to the problem motivation. Why is generative modeling required for TAD? Compared to object detection, action detection suffers from boundary ambiguity. For example, in a video of sumo fighting, annotator 1 and 2 may annotate the same sumo fighting class with different temporal boundaries. This process is stochastic and happens due to motion augmentation. Generative models can help solve this stochasticity. One simple way to adapt generative models is to adapt diffusion det for the task of TAD. However, diffusion det is a RCNN-based model which suffers from two-stage error propagation, less interactions among random bounding boxes and longer training times. One solution is to use DETA-style models for TAD. DETA-based models are single-stage, has interactions among the queries and also faster to converge if noise is added to the query. We can convert this discriminative DETA model into a generative DETA by converting the decoder into a denoiser. We can inject noise into the queries and iteratively denoise it. Adding noise to proposal makes us similar to stable diffusion-based noisy addition, where instead of proposals, noise is being added to the image latents. Now let us dive into diffusion models which drive our DiffTAD. The primary basis of diffusion model is to add noise into a clean image or proposal and make it indistinguishable from the original. This step is often called forward diffusion. In the next step, the model tries to reconstruct the same image by iteratively denoise the noisy image. This is referred to as reverse diffusion. In the forward process, random Gaussian noise like shifting and scaling is applied to ground truth action proposals in an iterative fashion. This helps us generate multiple noisy proposals from a single proposal. This has close association with how RPN works. In the reverse process, we pass in the video along with a sampled noisy proposal from the Gaussian distribution. Next, the denoiser takes in this noisy proposal and tries to denoise the proposal conditioned on the video. It is important to note that diffusion models works in the continuous representation space. However, our sampled noisy proposals are discrete. To convert them into a continuous space, we employ sinusoidal curve or MLP to project it into a continuous embedding. These noisy embeddings are then passed as queries to the DETA decoder, which is our denoiser. There are a lot of benefits of using DETA decoder as a denoiser. First, it speeds up training convergence by solving the Hungarian matching bottleneck. Secondly, proposals or labels can be conditioned either in query or as cross-attention modules without any design change. Thirdly, it is a NMS-free design, making it faster during inference than existing generative approaches. We also propose a new selective conditioning on the denoiser, replacing the self-attention block on the queries. It selectively refines which queries to denoise for the current time step based on signal from previous time step. We calculate the cosine similarity and IU overlap of both the current and previous time step. Based on this signal, we choose which proposals are most likely to be closer to ground truth and then denoise them. This makes the inference sampling stage faster and then helps us refine the proposals in a cascading fashion. Finally, we decode using the TAD heads for start, end of proposals, action class and proposal confidence scores. Thanks to our model design, we perform decoupled diffusion in both RGB and flow modality. We observe that decoupling the features help in solving the same denoising problem in different perspective, thus complementary in nature. Now let us look at some insights from DiffTAD. The first is one model multiple trade-off. As shown in the figure, discriminative models typically produce same output for multiple runs on the same video. Our generative variant, on the other hand, produces different output proposal each time the model is inferred for the same video. The second is faster convergence. As shown in the figure, our DiffTAD converges faster in training due to the solving the Hungarian matching bottleneck by adding jitter in the proposals as a part of reverse process denoising strategy. Lastly, it is sampling efficiency. Because of our inherent model design, we can obtain best performance with very less proposals as query, less number of denoising iterations and also low on memory. Now coming to quantitative results, our DiffTAD surpasses most of the discriminative learning competitors with just a single step denoising. However, with multiple steps it is the state of the art in both ActivityNet and FewMOS datasets. Now coming to ablation, we first evaluate the role of self-conditioning on the DiffTAD performance. We observe that it is a vital addition to our model design as shown in the table. We also observe that if we pass 70% of the proposals into self-conditioning, it gives us the best performance. Increasing the number of proposals and denoising steps indeed helps our model to obtain better performance, but it is interesting to note that it stagnates after 50 proposals and 20 denoising steps, justifying the effectivity of our denoiser model design. We also evaluate the importance of decoupled diffusion. As seen from the diagram, the RGB and flow diffusion branches capture complementary proposal representations, and when combined gives us the best performance by a large margin than early fusion. And with this we come to the end of the talk. Thank you for your patience and listening to this presentation. You can scan this QR code for the implementation of DiffTAD, and for any queries you can reach out to me in this email ID.